Distinguished colleagues, good morning. I will speak today about the trends and photogrammetric technologies. It's more fit for a scientific overview than a brief 20-minute presentation. Still, I would try to highlight some of the most important and telling trends that we observe at the moment on the market of the photogrammetric technologies. My task is getting easier because two of the most practically important issues on the current development will be the subjects of separate presentations. That is the building of 3D models. After my presentation, we'll hear a presentation from Viktor Adrov, which is specifically about the creation of 3D models, and tomorrow Andrei Sechin, also from our company, will tell you about photogrammetric processing in cloud. Now, I've highlighted some of the subjects that will be touched upon in my presentations that include factors influencing photogrammetric technologies and what is happening currently in neighboring industries and sectors that affect photogrammetry, like sensors and platforms, computer tools, development of algorithms, and the two things that I mentioned previously, photogrammetry in cloud and creation of 3D models. With all due respect, photogrammetry, of course, is not the goal in itself in the development of mankind. And photogrammetry was born and is developing, will develop, to serve the needs of the society in geospatial data. Photogrammetry is not developing in autonomy from others, but because of the progress in such neighboring technologies as sensors and platforms, computing capacities and algorithms of photogrammetric processing. Geodata, we observe an explosive growth of geodata. There are more and more of them, and they're acquired by different sensors. We see an ever-growing number of users of geodata, and we see more unprofessional users. We have an increase in the diversity and accessibility of means to work with geodata, all sorts of web services, smartphones, tablet PCs, virtual and augmented reality systems, and we see an increase in the diversity of the visualization of the data, like traditional paper-based maps, digital maps, orthophotos, digital elevation models of different types of 3D models, 3D geoinformation systems. Here I would like to note the advent of a totally new type of geospatial data users. That would be like smart machines, UAVs, which also require for their services geospatial data, and this data, the paper-based data will never fit for them. They need new forms of visualization, new digital reality, if you will, that we spoke about and referred to many times today, and that would be 3D based as well. Just an idea came to my head that maybe at one of the future conferences in this room we'll see representatives of these new users. What interesting things are happening in sensors and platforms over the past few years? I'd like to note that, at least based on our observations, spatial and radiometric resolution has reached its saturation, because even now the aerospatial acquisition equipment can get a few centimeter resolution in multiple bands, and for photogrammetry and topography it's not necessary to get high resolution. The obvious trend of recent years is the use of UAVs, or unmanned aerial systems, as the acquisition systems for small areas Now they use multi-camera systems more often, which aside from nadir images also acquire oblique imagery that allows us to get highly texturized 3D models, as well as helps us address more efficiently the cadastral tasks, because oblique images can get us much higher quality images. As for the remote sensing data acquired from space, we can say that we have a barrage growth of images because of, first of all, that not separate satellites are launched now, but the whole constellation of satellites are launched into space. As long as the photogrammetric technologies deal with huge volumes of data, and there's a need to do a lot of computation with this data, and naturally for the development of photogrammetric technologies, or photogrammetric technologies are affected by the development of the computing tools. First of all, for implementation of different algorithms, it's important how efficient processes are. They're distributed. Computing is important. The distribution can also allow for parallel computing, because some images or groups of images can be processed independent from each other, in parallel to each other. By increasing the capacities of processors, we can multiply their capacity like this. We need high storage capacity because of the big volumes of data, or big data, and because of the acquisition, reception, and distribution. It's becoming distributed. We need high communication speeds, especially online speeds. There are no problems with the use of distributed architectures and storage of big data, because these problems can be done extensively by attaching it to big servers or storage servers. As for processors and speed of communication or data sharing, I have a separate slide about this. No matter how strange it seems, but these two parameters that describe the behavior of these sophisticated technical systems like processors and digital networks like internet networks can be described by the law of Moore and law of Nielsen. Here you can see linear diagrams, because in one of the axes we use logarithmic scale. The Moore's law was formulated about 40 or even 50 years ago, and initially it stated that the productivity of processors, or capacity of processors, or the density of transistors per chip is growing, or is doubling every 2 years. The Nielsen's law happened a bit later, because internet appeared on the market a bit later than the processors, and Nielsen's law claims that the speed of data communication or data transition will increase by 50% every year. So as far as these two laws are concerned, there are two news here, one bad news and good news. Bad news is about Moore's law, is that in fact this law stayed true by decrease in size of some separate transistors and the increase of their number per chip. And now some elements of these transistors are close to atomeric size, and subsequent implementation of this law, Moore's law, can be physically impossible soon. And here we shouldn't expect some kind of breakthrough, maybe invention of new computers on new physical principles. like quantum computers that people have been discussing for a while now, and there are some experiments to develop such computers. As far as the Nielsen's law is concerned, everything is more or less within the expected parameters. The online speeds are growing, and in the next few years we are promised some online networks of the 5th generation 5G internet, which will have this transition speed of a few gigabits up to dozens of gigabits per second. What interesting things happened over the past 10 years in terms of development of algorithms for processing. Here I'd like to distinguish stereo matching algorithm structure for motion, which came from computer vision, and they allow us to find more reliably the dots on the overlapping images by ensuring higher reliability and accuracy and higher automatic capacity for triangulation processes. Because the modern 3D images have much higher overlap than their analog images, each point can be seen on much greater number of images and can be part of much higher number of equations, which again invariably increases the accuracy, and all the modern photogrammetric systems must use this advantage. It's now a tradition now to use dense 3D models, digital elevation models or digital terrain models, which can be acquired through the seeming global matching method, just like Professor Chekunish's presentation is called, like semi-global stereo matching. I think that's the name in Russian. And as long as to achieve the maximum capacity of processing, we use whenever possible distributed computation. And for that we need to have dedicated software that would take into consideration such forms of distributed computation architecture. And the software designed for the use on a single computer cannot be automatically converted to this distributed image processing. I can tell you for sure because it's based on our personal experience. I will speak about it later on, a bit later. Now a few examples of how these algorithms work. Here we can see dense digital surface models based on the aerial photographies. To your left you can see dense digital model of Jerusalem. You will see such models a few more times within this conference, and the town of Jerusalem as well in the course of our tour. This method of building dense models comes as a pleasant bonus, which helps us acquire the true orthophotos when the roofs of the buildings are projected on the foundations of those buildings. And here you can see example of made up of 3 images: the source images of the city, and you can see that I see that I'm already over time here, but on the right lower image the roofs are positioned exactly on top of the foundation. This method allows us to process not only stereo pair images, but also allows us to process multi-temporal images. Here you can see the digital terrain model based on the multi-temporal images of based on worldview images and GUI images images acquired in the course of 5 years, and based on those images we built this accurate and precise model. Now a few words about whether my time will stretch out enough about automation in photogrammetric processing. Now virtually all the processes of photogrammetric processing have been automated to a large extent, aside from the stereo interpretation of vectorization processes. Still, we undertake additional effort to do that as well, and some companies, including our company, offer some tools to increase the efficiency of stereo interpretation using all sorts of templates, like template roofs, when we don't need to measure all the points, all the elements of the roof, and it's enough to measure only some of them, and the remainder ones can be acquired based on simple geometry rules. Some companies are creating dense cloud points with the acquisition such things as lines, facets, and they also use templates to restore out of these graphic primitives geometric shapes. Such algorithms actually are providing relatively good results only for similar typical objects of the same shape and size. But not to narrow it down to automatization, as I said in the beginning, most of the processes are highly automated, which allows us to build highly automatic and highly efficient solutions if we have clearly defined source data and output products, and we have high capacity computers. Like for instance, we developed two such solutions, Photomatic Conveyor S for orthophoto for large areas based on satellite images of super high resolution, and the digital elevation terrain model. And recently we have improved this solution for the capacity to use also aerial photography and build digital terrain models based on that as well. And very briefly, we'll have separate presentations about that. Naturally, an issue of the use of cloud platforms is interesting for photogrammetric processing, because here we can find some obvious advantages, like more efficient access to limitless processing resources, efficient licensing models for the software which exist in the cloud platforms, and sometimes there we can also find data. We have some obvious deficiencies as well, like data secrecy, because not everybody wants to place their data that they paid money. Nobody wants to place that into the cloud, and sometimes, at least at first glance, we might have problems with huge volumes of data that need to migrate to the cloud and back. And Andrei Yurievich tomorrow in his presentation will tell you more about it. Now, I will just tell you that the next presentation will be dedicated to such important thing as creation of 3D models of different type based on different technologies. And some conclusions from what I've just said would be the following. The development of photogrammetric technology or photogrammetric technology progress depends on evolution of sensors and platforms, increase in productivity of computer tools, and new efficient algorithms. One of the directions of photogrammetric technology development is the development of special high productive solutions for fully automatic creation of such products as orthomosaics, terrain models, and 3D models. Also, we see a lot of big future with the development of cloud technologies. And finally, as we will see from this subsequent presentation, modern photogrammetric algorithms allow us to create accurate and detailed 3D models of cities and objects based on different technologies. And in conclusion, because we've seen what was happening in the past 10 years. It would be, I think, interesting to try within this conference, within our roundtable that we'll have on Wednesday, see what lies ahead of us, whether we'll have stratospheric UAVs, when shall we see the qualitative leap in the computer technologies, whether we'll have a real artificial intelligence developed which will be able to do it with high precision level like human operators, and whether there will be a 4D real-time model development which can be updatable in real time because of the on-time updating of the source data. That's all I had to tell you. Thank you very much. I can take your questions either now or later.